All right, what's in the bag? Looks pretty tiny. Actually, there was two of them. I bought two. They're no longer manufactured, but DigiKey had a couple in stock. And so what are they? Well, they're crystal oscillators. They're little tiny crystal oscillators. And here is the data sheet. It is a low voltage PECL, okay? So what is low voltage positive ECL, emitter coupled logic. So low voltage positive emitter coupled logic. That's a mouthful, but it's just LVPECL. So why did I get this? Well, it had to do with the specification. I was looking to generate a square wave with a very fast rise time. I've generated pulses, but I don't like pulses. I like when the waveform goes up to a particular value and stays there, and I can watch the ringing and settling and stuff. The pulses get integrated, and I don't know, they seem to confuse the issue. So I wanted a nice square wave. A friend of mine pointed this part out to me, the guy with the VNA. Let's see here. Where's the specs? Parameters, blah, 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 blah. Yeah, here it is. All right, so this is why, so this particular crystal is 106 megahertz. So the oscillator, I should say, 106 megahertz. There's a big series of them. But I bought it because of this spec right here, 400 picoseconds. So the rise time is 400 picoseconds maximum. So it's better than that. And this is the 20%, 80%. 20%, 80% rise time. All right, so here's the package pinout. It's a 6-pin package. I don't know what ED is. Enable, disable. Okay, 0 is disabled. Enable is 1. So we'll just type in 1 high, ground, VCC, and then it is a differential output. Okay, so for noise reasons and stuff, it's differential. Most of the time, these are sent out on 50 ohm impedance lines. So it's 50 ohm impedance, and they're terminated with 50 ohms, and they're terminated to a voltage. They're not terminated to ground. They're terminated to 1.3 volts. And so it's a 3.3 volt part, and you reference them to 2 volts below the VDD, so it's 1.3 volts. You don't have to, this is like for, you know, this is the way they're characterized and everything. You don't exactly have to do it this way. You can put an extra, you can just put in a 50 ohm load down here to ground 2, and then they kind of self-level themselves out to 1.3. I'll probably just do that. I don't need a transmission to be accurate. I just need an edge, so I think I'll be able to do that. But there are these funny little surface mount parts, so I need to be able to breadboard this thing. So what I did was I took, I'll put some pictures here. I took the little part out, and I'll show you that. Cute little part, and you can see the underside here. It's got the little 6 pins, and they're spaced pretty far apart. So I'm going to be able to use the little adapter board that I have. And I think it'll fit on there just fine. It'll share pins, but I think the pin out and everything, I think it'll be fine. I'll get 2 lines out per pin. I think it'll work out great. So let me put it in the oven, and this is what it looks like when it comes back. And it's exactly what I thought. You kind of like share double pins, and this is what the final thing looks like. And now we're back, and yeah, here it is. Can I zoom in further? No, that's about it. See, they're tiny. So now I have a little dip part that I can use on a breadboard. Excellent. So that'll be my next project. And the reason I want to try to use this part is for the fast stage, is to use it for determining bandwidth of scope probes and oscilloscopes and stuff, since it should be faster than anything I've got. The fastest scope probe I have is 700 picoseconds, and this is about half of that, so should be good to go. Okay, so the next thing we need to do is terminate the output. So it's a differential signal is a plus and a minus signal, and sometimes drawn this way. And these two signals are 50 ohm impedances, and they need to be terminated at the other end. So the usual way of terminating them is with a 50 ohm resistor to 1.3 volts. It's 2 volts below the upper 3.3, so 1.3 volts. And you need to, whatever you do on this side, you need to do on that side as well. So there'd be a 50 ohm load to 1.3, and on the other one there'd be a 50 ohm to 1.3. You need both of them, okay? The Thevenin equivalent would be to do something like this. There's 2 values of resistors you can put in here, 1 to 3.3 and 1 to ground, and that would also be the same as doing this. You can work out the math, and that was the same. There's another one that I've seen where you take one side and you take the other side. Okay, so this is 50 ohms and this is 50 ohms, and you tie them together. Now why would you tie them together? Well, remember, one is plus and one is minus, so when they add together, they end in the middle point, and that middle point is this 1.3 volts. So this kind of automatically sets the middle point, but you still need to reference that middle point down because of the voltage and stuff. So then they put in a third 50 ohm resistor to ground, okay? And this one seemed really easy to implement, so I thought I would try that out. I did try just 50 ohm resistors to ground. You do get a signal out. There is some ringing on the signal. It's not damped. It's not exactly 50 ohms in the impedance system and everything, so it does give you some ringing. I wanted the best looking square wave I could get, so this one actually seemed to work out quite good. It's over here now. I'll put in a picture here, and you can see I have 2 tiny little 50 ohm resistor, 50 ohm surface mount resistor soldered on to the input and output, and those are tied over to a signal where there's another 50 ohm. They go into a wire, and there's another 50 ohm to ground. So everything is all in one little package here. I'm trying to keep lead inductances as low as I can. All right. So this is what I then end up with, and there's glare on the oh, that would have made it worse. There's glare on the, there we go, on the scope as usual. All right, so I'm getting a pretty nice looking square wave, and with a scope probe, with the Rigol scope probe in there, I'm getting 880 picoseconds, which I'm very, very pleased with. 880 picoseconds seems to be very, very good. So let's see here. What do I want to do? I want to test the HP probe out. All right, so I'm going to get out the HP probe, which is supposed to be faster, although I haven't really found the official specs for the Rigol one, but let me see what I can do here. I need to rearrange things a bit here. This is going to be complicated. If I go here, and I grab this, let's do run stop, turn the reference on. So that's, I have the reference. I saved the last picture, which was the Rigol probe. And if I bring in the, yeah, it's a little bit slower. So let me get the leads as short as I can here. Yeah, there we go. So let me save that one. All right, so you can see that an official mathematical measurement says that the HP one is about 100 is about 100 picoseconds slower than the Rigol one, but then you look at them just on the graph, and part of that may be just that the Rigol has some overshoot, and that extends the signal. And when you're doing a 20%, 80%, that can kind of fudge the numbers a bit, whereas the Hewlett-Packard one is flatter in response. So maybe it's a better probe because it doesn't overshoot. Maybe it's better critically damped. So my takeaway is those two probes are just as good as each other. You can use either one just fine. So my first initial thoughts of trying to buy a more expensive probe to try to make the scope work better seems to be false. It seems to be that the probes that come with the scope are just fine, if not spectacular. So yeah, go Rigol. Anyway, I now have a way of generating a probably around a 300 picosecond edge right now, and it's a nice square wave edge too. It's not a pulse; it's a square wave edge. So I'm able to do these types of measurements, which I like better. The other thing that you're looking for in scope probes is, do they accurately represent the voltages? It's supposed to be a 10-to-1 probe, so the 10-to-1 ratio in the probe needs to be exact. In fact, most of them have an adjustment inside to make sure that is exact. And these two seem to be pretty accurate in the voltages. When it finally does settle down, they seem to be ending up about the same places. So both of them seem to have a pretty 10-to-1 ratio in them. Okay, let's do some heads-up comparisons. All right, so the first thing we'll do is run the Rigol probe. Okay, so I'm going to put the Rigol probe on, and you can see we get a trace there, and I already have stored that as a reference. So Rigol is going to be our reference. Let's try the fancy HP 50 megahertz scope probe. Let's put that on, and we get basically the same thing with less ringing. Okay, so I think maybe the HP one is more damped at 500 megahertz, and it looks to be about the same speed. So I would call those about the same. Okay, that was the HP one. All right, so let's try a Tektronix probe that, let's see, this Tektronix probe is the P6112. It's claimed to be a 100 megahertz probe. So Tektronix says this is only a 100 megahertz probe, so let's put it on. And I don't know, it looks fine to me. These tests are just driving me insane. So this is the 100 megahertz Tek probe. I don't know, looks Jim Dandy to me. Does anybody say that anymore? Jim Dandy? All right. And then let's try the super cheapy probe that came with the Mustool, the battery-powered soap, the little portable one. This has got to be the world's cheapest oscilloscope probe. And whoa, okay, so it's bad. It's got really bad ringing in it. Okay, so there we go. At least one cheap probe says no go. All right, so yeah, you definitely don't want to use this one. It's got wacky ringing. If you just did an edge test on it though, it would look good. So that's why I wanted the square wave. Remember I said I didn't like pulses. I like to have the thing stay high. So if you were just doing a pulse test, this would accurately represent the pulse, but then you would lose the information about its really bad edge retention and stuff, right? So yeah, this is why you do a square wave test in my book. All right, so that probe is bad. Where's my other probes? I think I already put them away. Let me go find them. All right, I've got 3 other probes here. Sorry about that. The next one's going to be another Hewlett-Packard probe. This is the little tiny one. This is a 10017A. This is claimed to have 275 megahertz bandwidth with a particular oscilloscope. So it was specified as a combo pack, as a system thing, not a individual probe thing. So yeah, this one looks pretty good too. It seems to be a little short on that edge. Maybe I'm looking at a different, let me try this one over here. Yeah, I think it was that one. Yeah, there we go. I was looking at the minus output instead of the plus output. So yeah, same thing. It does have a little bit of ringing, but I would say, yeah, this is a plenty fast probe. So again, they didn't test the probe individually, they said with a system. So they were selling a 350 megahertz scope or 275 megahertz scope at the time, and they said, yeah, this probe is as good as it needs to be, but it didn't say how fast it could go, because oscilloscopes weren't any faster than that back then. So yeah, this probe is very nice. Okay, let's do, I have 2 more two more Tek probes, all right? Let me get the first one out here. I've got it. There we go. Okay, so this one is a, oh, this is a famous one. This is a P2200, okay? A lot of Asian scope manufacturers name their probes after this one. Yeah, this is a nice one. Let's give that a try. And there you go, it's beautiful, right? And this one claims to be, I think, a 200 megahertz probe, but I don't know, it looks good to me. And then the final probe is a really old school Tek probe. This one here, if you remember that one, it is a P6106. P6106. I don't remember the specs on this. I think it's pretty good, but definitely old school. I think it's 250 megahertz if I remember right. I don't remember. Anyway, let's put it on. See how he does. Look at that. Look at that. I think actually, you know, if I didn't know about ringing, I mean, I don't know what the truth is, right? But this one looks like a nice roundy wave, and it looks very slow on the edge. Okay, so the edge looks very, very slow. So yeah, so this one is a slow probe. This one's definitely a slow probe. Okay, so this one fails. This one fails. Yeah, very, very slow. Very, very slow uptake. The I can turn on the measure here. Measure, add, rise time. Get rid of that. Here's the rise time. I can read it. Yeah, this one's really slow. This one is 1.25 nanoseconds, right? So very, very slow probe. The other ones are, you know, in the 800 picosecond range. All right, so now that I have that edge there, let's go back and look at a couple of them. Let's go back and look at the which one's on top? Let's look at this the HP one. This one, I mean the Tektronix one. This one's supposed to be a 100 megahertz probe. 6112. Let's measure its rise time. Yeah, it's measuring, I don't know, at best like 1.15. Something like that. It's a bit noisy. All right. Let's see here. Let's go back to the tiny HP one. See what kind of rise time we get out of him. Oops. It's hard to get this one grounded. It doesn't have a good way of holding on the collar ground. There we go. Look at that. 69 picoseconds. What? 609. This one's fast. This little puppy's fast. Yeah, 700. Wow, jumping around, but 700 picoseconds for this one. Yikes. It's maybe because it's so damn small. It helps with fast edges and stuff. So that's interesting. All right, and we'll go back to the 500 megahertz HP probe. I'll read the part number 1073B. 173B. It's measuring around. It's jumping around as well. Let me turn on averaging so I won't jump around so much here. Averaging, let's average like, I don't know, 16 or something. That's probably okay. Yeah, I'd say somewhere around 930 picoseconds. And we'll go back to the trusty Rigol probe. And it's measuring around 900 and It's around 1 nanosecond. Okay, so, well, maybe the HP probe is just slightly better in rise time. Slightly better in rise time. With an official measurement, right? If you were just looking at traces on the scope, they're kind of equivalent. And maybe the H one does squeak it out just a little bit, which I thought it probably would. It's just barely better, if anything. I think under different conditions, the Rigol seems to be better. In other conditions, the HP seems to be better. The HP seems to have less ringing, but the Rigol ones seems to be fine. So yeah, go anyway. You make your own judgments of which probe was better. But in my book, yeah, I'm impressed with the little HP one. I kind of was wondering about that one because at the time these little probes, they don't make these anymore. The time that they were making these little probes, 275 was as fast as their scopes went, I think. At least what these were sold with. And if you put it on a 350 megahertz scope, yeah, the system definitely gets better, right? So there you go.